So let me briefly mention the most important point we arrived last class is that for any physical process, decay or scattering that happen in nature, all the following quantities are separately conserved. And for any interaction which does not happen in nature or never found to happen in nature, at least one of the conservation laws must be violated. And these are the quantities which are conserved for processes that happen in nature. So these are electron-lepton number, which is an intrinsic quantity, muon-lepton number, an intrinsic quantity of the particle, tau lepton number, which is also an intrinsic. So there are three lepton numbers corresponding to three kinds of leptons, E, mu, and tau. There are baryon number, which is 0 for leptons, but non-zero for at least quarks. So far we have seen in the list. Electric charge is another intrinsic parameter, which did not have to be associated by looking at the interactions like we did for lepton numbers, but it was there from the very early stage of development of science. Similarly, spin, angular momentum. So these first six are intrinsic quantum numbers, and there are other two extrinsic quantum number or extrinsic numbers, parameters associated with the particle. We don't call it explicitly as quantum numbers, but we call them external parameters or extrinsic parameters associated with these particles. They are total linear momentum, which must be conserved in any process that occurs in nature. And since total linear momentum is a vector quantity, it has three Cartesian components. All the three components are individually conserved. Okay, so sum of px of all the particles of initial state should be equal to sum of px of all the particles of final state. Clear? Similarly, sum of py is equal to sum of py, initial and final, similarly for pz. And also total energy of this particle should be conserved. Just a minute. Okay. Now, to tell you is that you see that in this list of these 8 quantities, rest mass of the individual particles, their sum of rest masses of the particles of initial state did not be equal to sum of rest masses of the particles of the final state. Rest mass is not conserved in a process even though it is physically occurring. Okay. And in any process which does not occur in nature, at least any one of these 8 quantities, any 8 conservations should be violated, at least. And since rest mass is something which is intrinsic to the particle, given a particular particle, rest mass is unique to it, but the energy and momentum is related to rest mass by the relation E equal to P square plus m square square root that I showed earlier here, this quantity. So here, out of the 3 components and energy, only 3 are independent. Out of these 4 numbers, only 3 are independent. Okay, if you tell three components, other one will be automatically determined by this. In that sense, there are 3 numbers associated with energy and momentum, 3 independent numbers. So if you think in terms of independent quantities which are conserved separately for all processes happening in nature, so there are these first 6 intrinsic quantum numbers, and 7, 8 out of this energy and momentum, there are 3 numbers. So far we discussed 6 plus 3 equal to 9. Total 9 quantities has to be conserved. There are also subtle important quantities which we will discuss in time to come. whose conservation or non-conservation in a physical process will have very uh, will be significant in determining what kind of interaction it is. We will see that later, but for the time being, we are just starting our today's lecture by saying that there are these 6 plus 9 independent quantities which are conserved in all processes happening in nature. Okay, so this was our bottom line from yesterday's class. Clear? Okay. Now, let's see a discussion. Let's begin a discussion. So what is the end result of the discussion? We will see soon. But to start with, think of an arbitrary or a general process. Okay, this process, this looks like a scattering because initially, at the initial state, there are 2 particles. It could have been a decay if there is 1 particle at the final state. So this represents any general process. I have to write one thing, so I have written scattering. You could have the same logic will be applied to even if it is a decay. Okay. Okay. Now look at this. Say, let's see that this just a minute. This interaction happens in nature. Just a minute. Sorry to disturb. I saw a mail. I saw a chat. Somebody is saying Vidisha is not able to join. Is this because of a technical problem or because of her own problems? She will not attend the class. Amali? Oh, connection problem. Okay. Okay, let's see. So when she will come, I will put her in. Okay. Anyway, let's continue. So this is a process. So this is a decay process, a scattering process, which happens in nature. Suppose X is a quantity which is X is any intrinsic quantity belonging to this set of intrinsic quantum numbers, not involving energy and momentum. So X can be any either charge or baryon number or lepton number, but for the time being, X is not the energy and momentum. Okay. Now, since this process, okay, so what have I done? So let's omit E. So don't complicate it. I have done with 4 particles. So there are 4 particles A, B going to C and D. Now, since X is an intrinsic quantity, it should be conserved for this naturally occurring process. That means X for X of A plus X of B should be X of C plus X of D. This is the conservation law for that particular quantum number X, say lepton number or baryon number, whatever it may be. Now, see the argument, very interesting argument, simple argument. If XA, XB, XC, XD, they represent values of a particular quantum number for particles A, B, C, and D respectively, then the values of the quantum numbers for their respective antiparticles, A bar, B bar, C bar, are minus XA, minus XB, minus XC, etc. Clear? Because particles and antiparticles have their intrinsic quantum numbers just opposite in sign. This will not be true for extrinsic quantum numbers like energy or momentum. A particle can have any momentum, as antiparticle can have any momentum. But so far as intrinsic quantities are concerned, particle and antiparticle in quantum numbers are just opposite in sign and same in magnitude. Now, so A, B, C, D have these quantum numbers. my A bar, B bar, C bar have these my negative quantum numbers, negative values corresponding with respect to A, B, C values. Now, the validity of equation, equation 3. Validity of equation 3 would also imply the validity of any of the following sets of equation. Because A, B, C, D, they are obtained by just taking any one parameter this side with a negative sign and other from this to this side by putting a negative sign. Okay, just exchanging the terms from this side to this side simply algebraically. These are just mere numbers. So you can write this equation 3 in terms of A, B, C, or D, and like there are other possibilities. Now look at what does A represents. This particular form A, which is if this equation is valid, which is valid because A, B, C, D is a naturally occurring reaction in found in nature. If for that quantum number is conserved, so this is valid. If this is valid, this is mathematically valid, algebraically valid, then this means this equation A stands for the conservation equation for this quantum number X, where A particle is interacting with C bar going to B bar plus D. Okay, because minus X and minus XC and minus XB are value of the quantum number X for particles C bar and D bar. Just a minute. Sorry, I have to take a call. Okay, so is this clear what I was saying, that X, A, B, C, D are just different appearances of the same equation, but they therefore represents, A represents this interaction, because A can be seen as the conservation law for X for this equation, because A plus C bar goes to minus XC, B bar is minus XD, D is XD, and this B is for this because C bar has a quantum number minus XC, A bar has a quantum number minus XA. Okay, so on. So what does this say? Since this is valid, all these are valid, that means these reactions will also happen in nature. So the final conclusion is, if this interaction channel is observed to happen in nature, then all the corresponding crossed processes, by crossed processes I mean these processes, some of them I have written, where you can take one, you can interchange the particles from right to left or left to right by making them their corresponding antiparticles. It is algebraically equivalent to interchanging terms from right to left side by putting a minus sign in front. In terms of particle interactions, that is equivalent to this fact that if this reaction is found to happen in nature, that means all quantum numbers are conserved because of the fact that particles and antiparticles have equal and opposite quantum numbers, opposite sign. Then for this processes also, which are obtained from this by interchanging particles from this side to this side and making antiparticles, for all these processes, quantum number should always be conserved. All quantum numbers should always be conserved if it is conserved for this, because of this obvious reasoning. Is it clear?
Yes, sir.
Therefore, this, so we say that the way we have assigned quantum numbers and the fact that every particle has its own antiparticle, and by our principle, by our scheme of assignment of quantum numbers to different particles, each particle, an antiparticle, acquires quantum numbers opposite in sign. Because of the fact, if this process happens in nature, all the this kind of processes will happen in nature. There is no restriction on these processes to happen. These are called crossed processes. Crossed means in that sense, it is, you are taking this side or this side, but remember, if you are interchanging sides of the particle, they should appear as antiparticle. Okay, but there is only one restriction. This all processes should happen provided they are energetically viable. Means provided energy momentum conservation holds for them, because for a natural reaction to happen, energy momentum conservation along with the other quantum number conservation should also hold. Therefore, from an intrinsic quantum number conservation, we can say that these processes will happen in nature. Only thing is that they have to be suitable energies so that you can apply, if you see, energy momentum should be additionally conserved. Okay, and this kind of symmetry, that if this happens, all these will happen, or occurrence of any reaction in nature amounts to occurrence of any reaction of this set. This is a kind of symmetry. Looking at one equation, one interaction, you can comment on possibility of other kinds of interactions of this set. So all these interactions of this represented by the whole set, including this, are called interactions which are connected by crossing symmetry. Okay. To give you an example, if you look at this reaction, muon decay that I discussed in last class, if muon decays along this path, all quantum numbers are conserved, intrinsic quantum numbers are conserved, energy momentum has also to be conserved separately, spin also. Then these processes which are obtained by interchanging particles from one side to other side and changing it to its antiparticle. Okay, so for example, this one you can easily see is just similar to this. Only thing is that one particle is exchanged from left to right by making it antiparticle. Similarly, this equation, all this process should happen in nature so far as intrinsic quantum number conservation is concerned. Okay. Only if they will not happen if energy momentum conservation doesn't hold for them. And there is one particular reaction, which is this reaction, which is just same as this. Just you, what is this? So you have interchanged mu to this side, electron to this side, making their antiparticle. So E plus going to mu plus and others this. So this decay is never observed in nature. Okay, this decay is never observed in nature, though quantum numbers are intrinsic quantum numbers are conserved. All the intrinsic quantum numbers are conserved. So though this is related to this process by a crossing symmetry, still it does not happen, because you can never satisfy energy momentum conservation with these particles, because their rest masses are such that because a less massive particle cannot decay to higher particles, you cannot satisfy energy and momentum conservation separately. Okay, we will see this more in detail later. But all these reactions hit here, it will happen. Only thing is that you remember, I have given a star in the last two reactions. Here, what happens? This one electron neutrino, one anti-muon neutrino are interacting to give you this. Now, this is not a decay, this is a scattering process, but related to this process by crossing symmetry. In this process, you can see that initial state particles like neutrinos are very uh, uh, light, or they have very small masses compared to muon masses. They are of the order of MeVs. They are the electron neutrino masses, say, of the order of eV. So from very low rest masses, high rest mass can be produced if these two particles carry very high momentum. So suppose mu E and mu comes from opposite direction with a very high momentum, super high momentum, so that their total energy can be equated with the high rest mass energy plus their less momentum kinetic energy of these particles. So this is technically possible, but you have to have very high energy. You have to impart to the neutrinos. But in this reaction, whatever energy you impart to electron, you cannot carry, this decay can never be carried out. Energy momentum conservation can never be satisfied in this channel. Okay, because there is simply one particle in the universe, one particle in the initial state, and it will always decay. So whatever, how much energy you give it, mu will carry that energy, but its mass is much less than this. We will see that why this can't happen. Energy, why this, for this, if you can see this, because it is easy to see if you go into the rest frame of this positron, then total energy, it has just mass of positron or electron. That single energy cannot, that small amount of energy equal to electron mass cannot produce more masses plus more kinetic energy. Everything is greater than this mass. Okay, so you cannot conserve energy for this process. Similarly, the other process, last one, that is also where I have taken all these three particles to the left side by making them antiparticle, and this to the right side by making them particle. This can also happen in nature because all quantum numbers are conserved. And it is possible to conserve energy momentum also because E plus have less energy, but they can carry high kinetic energies. So together, this muon mass can become generated. But in reality, it is difficult to happen because it is very unlikely, very less probable for these three particles to come together for a reaction. The probability of coming two particles together in close proximity to initiate a reaction is much greater than probability for coming three particles together. Probability for coming four particles together are much less. So this has much less probability, so it may be very difficult to observe. But so far as energy momentum conservation and other quantum number conservations are concerned, all these reactions can happen in nature. Only this is not happen because you can never conserve energy momentum in this case. Is it clear?
Yes, sir.
Okay. Let me move to next slide. So to summarize again, so this is the same page I've written here. For every physical process that will happen in nature, the following quantities are conserved, and for any interaction channel that does not happen in nature, at least one of them should be violated. So there are 8 such quantities. Now, there are some crucial aspects of this. Just a minute. You have to note that note that among these above mentioned 8 parameters or 10 parameters, if you consider independent parameters among energy and momentum, among these parameters associated with each particle, energy and momentum are not intrinsic to the particle. Okay, so each particle with its characteristic unique intrinsic quantum numbers can carry any energy and momentum P subject to the constraint this. Okay, so any particle with their own unique set of quantum numbers can carry any energy and momentum, but they are denoted by this means there is one constraint on the values of energies and momentums by this equation, but this is true only for massive particles. For photon, energy momentum relation is just this. Okay, you all know E equal to P into C. I am assuming C equal to 1 for all cases. M is the rest mass of the particle. So there is a constraint on energy momentum. So far as this constraint is respected, particle can have any energy and momentum. They are not unique to the particles. Moreover, there is an important aspect in suitably designed experimental setups. Momentum and hence energy carried by the particle can be controlled externally. Okay. Or in naturally occurring processes where you don't have any control, it just occurs in nature. Depending on the process involved, the particles may be produced with different momentum and energy. Okay, so there are spontaneous processes in ongoing processes in nature, like nuclear reactions going inside sun. You have no control over that. In that, all different particles or neutrinos are produced, electrons are produced with different energies depending on from which reaction they are produced. So they can carry same electron. An electron can carry different energies depending on the ambience where they are produced, or even if you produce them in the laboratory, you can have a control how much energy or momentum you need to impart to the fundamental particles you want to impart. Okay, so this energy and momentum are the only parameters which can be controlled in some cases. In the laboratory, we have the only control over energy and momentum parameters, momentum quantities carried by a particle, but not on the intrinsic parameters. You can't change lepton number of a particle. If it changes, the particle changes. Okay, so that is not in your hand. Okay, so energy and momentum are two important aspects carried by associated with the particle which can be controlled. Now, our next coming discussion will be on this energy and momentum. So let us put aside discussion on intrinsic quantum numbers, lepton numbers we were discussing so far for the time being, and let us discuss how to deal with these energy momentum conservations for any processes, how to handle that. Then we will come back to again to intrinsic quantum numbers, then discuss baryon numbers and other numbers. Lepton numbers we have discussed enough so far. Okay, so we will discuss now this relativistic kinematics. Kinematics means discussion of energy momentum of the particles involved in the interaction, and in this interaction most all the particles are we assume to be relativistic because they are microscopic particles, they have very high speed. So consider a general decay process like A going to B, C, D, or side by side simultaneously a general scattering process. Today I will take, not take a long class. I will finish after a short while, just because this aspect I will only discuss. So consider a general decay or a general scattering. So any general process, it may be a decay, it may be a scattering. So we want to see how we have to handle the energy momentum conservation relations for these systems. Okay, this is all known to you, just look at it. So whatever be the process, suppose now energy momentum of these particles can be represented by a 4 vector. This is another notation, 4 vector momentum for vector is zeroth component is energy, and space other three components are linear momentum. Okay. Usually it is written as E by C into PC, but C is 1, so I am writing just E comma A, E comma P. Okay. So this is the 4 vector for momentum, 4 momentum for all these 4 particles. If you want to see separately, these and these are energy and linear momentum of individual particles. Okay. I am just using both these notations because you will see in books both kinds of approach. I mean, both ways of doing this. Okay. Now, if MA, MB, MC, MD are rest masses of these particles A, B, C, D, whether in this process or this process. So far as individual particle masses are this, that means P mu, which is, you know this, we have studied relativity, is a sum over mu from 0 to 3, is basically E square minus P square. Okay, the metric is Minkowskian, so E square minus P square, which is equal to the rest mass square. Okay, or in other words, E is this. So while applying the energy momentum conservation to these equations, you can use 4 vector notation or simple this separately energy and momentum relations. Okay. Now, the simultaneous conservation of energy and momentum in the process can be written as this. Okay, because if energy and momentum are conserved, then the 4 momentum for all these processes will be, for the decay channel will be this, and the conservation of 4 momentum for the scattering channel will be this, because its 0th component corresponds to energy conservation and its other 3 components corresponding to components of momentum conservation. And this is obvious. For scattering, only A goes to B, C, D, and for decay, and for scattering, A, B goes to C, D. Okay, so these 2 equations, or you can look at separately. These are simple equations. You can look this separately as, for decay channel, this vector sum of momentum, and this for scattering channel, this vector sum of momentum. These 2 equations represent the conservation of momentum. And for energy conservation, for decay channel, this is the energy conservation. For scattering channel, this is the energy conservation, for obvious reason, because 2 particles in initial and 2 particles in final state for scattering. Now, for decay channel, in place of this, you can put the total energy. So this gives you the energy, this gives you the energy conservation, and this gives you the form of energy conservation for decay and scattering channels. Okay, these are very straightforward equations. So these 2 are energy conservation equations. These 2 are momentum conservation equations. Clear? So you all know this from relativity. I have just applied for a decay or scattering process. Now, is in the description of energy and momentum, the choice of reference frame plays an important role in simplifying your problem. Now remember the basic fact that occurrence of any interaction or any intrinsic quantum number values or intrinsic attributes of any particles of the system has nothing to do with your coordinate system or frame of reference. So if a muon decays, whatever be your frame of reference, it decays to electron, muon, neutrino, and anti-electron neutrino. Okay. So the process itself or the intrinsic quantum numbers of the particles involved in the process in no way depends on the observer's position of observation. Okay, or in other words, the reference frame. What depends on reference frame are the quantities which are scalars and vectors or tensors like that, because they depend on coordinate transformation. Intrinsic quantum numbers, neither these fundamental process itself depend on choice of observers frame of reference. Okay, so the description of extrinsic attributes of any system, which are extrinsic attributes means the position, the time of occurrence of the event, or the energy of the system, the momentum of the system, they depend on the frame of reference. Okay, so E and P, energy and momentum, depends on choice of frame of reference. But again, these quantities, E square minus P square, is again rest mass square. Rest mass again does not depend on frame of reference, because rest mass is something intrinsic to the system. Okay. So, but E and P are dependent. So, in terms of E and P, E square minus P square is a scalar quantity. It does not depend on coordinate transformation that way. Anyway, but we exploit this aspect of frame independence of basic fundamental processes and intrinsic quantum number, but dependence on extrinsic parameters. We use this to study the kinematics of interactions and conveniently chosen frame of reference. We can conveniently choose the frame of reference where we can write down the equations of conservation for energy and momentum more in a relatively simpler form than in any general frame. Okay. Say for this, now for this decay channel AB, where there is one particle is in the initial state, a convenient frame of reference where these equations representing conservation of momentum and energy and their visualizations take relatively simpler form than in a general frame is the rest frame of the decaying particle. Because you want to see the decay, if you are only involved in the basic process of the decay, underlying process of the decay, just you have to choose any reference frame. In all reference frame, the decay happens anyway. So it is better to simplify your parameters in your appearing, which will appear in your description, by choosing the reference frame suitably. Like for describing particle moving in a straight line, you always choose the x-axis along the line. Okay, so that it is described by just x of t, yt and zt are constants. Similarly, in this case, you choose the rest frame of the decaying particle. That is the most convenient frame where equations which will represent the energy momentum conservation, at least, they will get simpler form because of the simple reason that in the rest frame of the particle, linear momentum of the particle is 0. PA is 0. This is the frame. Okay. If PA is 0, that means the truth with respect to the observer, A is at rest. And you are observing this a decay of this particle at rest to particles B, C, D. Okay. For scattering channels, where there are two fundamental particles, there can be two types of convenient frames depending on what what you want to look or what is your preference of or what should I say? What you want to determine about the system, depending on that, you choose your reference frame conveniently. So one such convenient frame is center of momentum frame, which is by definition is the fact that this is a frame where both A and B, the total initial state, have zero momentum, meaning this is the center of momentum frame. A and B, total momentum of the initial states is 0. Okay. So this means what? This means A and B are approaching each other from opposite sides. So that EA vector is just opposite sign of PB vector and they have equal in magnitude. So they are approaching, A and B are approaching towards as if to collide with each other from opposite sides. So this is the frame of reference. The initial setup is like this. Your laboratory, you can make this setup by, if you want to see interactions of A and B or scattering of A and B, you just create two beams of A and B and collimate them in a way that they just approach each other and head-on collision without any angle between them. I mean, with only 180-degree angle between these two directions. Okay. So this is the center of momentum frame. Other frame is the laboratory frame, where you want to see this interaction, where you have one target particle A, which is at rest. One particle is at rest, and the other particle is incident on this target. So PA is 0, PB is non-zero. This is the setup of a standard target and incident particle setup. And this is the setup for two beam colliding with each other setup. Okay, these two kinds of setup can give us two different frames to observe a process. Okay, so these are the different ways of choosing frames of reference, convenient frames of reference to describe energy momentum conservation for this process. Okay, so let's apply energy momentum conservation for the decay channel in the rest frame of the initial particles that I discussed here. Okay, in this frame. So decay is done only in the rest frame of the particle. So if we have, so rest frame is PA equal to 0. So momentum conservation is PA is equal to PB, PC, PD. So this is the momentum conservation. PA is 0. Final momentum sum should also be 0, which may also imply this. Okay. If you want to look at a picture, this is this. This is this particle A sitting here. PA is 0, and BCD, PB, PC, PD, they are vectors of the decay products, momentum vectors of the decay products. They should be directed in such a way their vector sum should be 0. That means they should be directed, suppose in this way, so that if you put them together, they form the sides of a triangle. Their sum is 0. Okay. So PB, PC, PD in the same order gives you 0 vector. This is for if you see the decay in rest frame of this A particle. So A particle is at rest. A, B, C, D are product particles with this energy momentum conservation gives you this equation, this picture, or this equation, whatever you say. Now energy conservation for this frame where PA equal to 0, and for energy conservation we can also apply this equation because we have already seen this for the rest frame decay. So this equation 7. So this is the energy conservation, general energy conservation law. Here put PA equal to 0, and for PB you can put minus PC PD. So this equation, look at this equation. MA is equal to, in place of PB you can put PC plus PD whole square plus MB square plus the other two terms. Okay, so the whole energy momentum equation, this or this is just an expansion of this. Rest masses of the particles are known, suppose, then this equation you have only two vector momentas, PC and PD, connected by one equation. Okay, this PA is eliminated because of this choice of the reference frame, and PB also got eliminated for the same reason, just because in this frame PB can be expressed as PC plus PD from momentum conservation. Okay, so the final expression for energy conservation does not have PB.
That should be PD.
Yeah, sorry. This should be PD. Thank you. Okay, actually I am telling you because saying all this because at some point of time we will solve problems where we have to exploit these equations, and then we have to choose which reference frame the energy momentum conservation takes the most simpler form. For decay, so usually this is the most convenient frame, the rest frame of the initial particle. Now for scattering, let's take the center of momentum frame first. Center of momentum frame means total initial momentum PA plus PB is 0, which is this picture. A and B are approaching towards each other. These vectors are momentum vectors for A and B. A and B are approaching towards each other initially. So vector PA is equal to minus of vector PB. Okay. So energy momentum conservation gives you, so this gives you this. And since energy momentum conservation, PA plus PB is equal to PC plus PD. So this is also 0. Therefore, we have PC equal to minus PD. Okay. Therefore, this PC vector, the outgoing particle C, will have same but opposite momentum to that of D in this frame. Okay. This is a very advantage of this frame. But there is no link between energy momentum conservation does not put any constraint on the angle between PA and PC. So you can't say in which direction the outgoing particle goes. This can go in this direction or this direction. Only thing is that this and this should be oppositely directed. Okay. But what is the angle? That can't be, that is not restricted by just energy momentum conservation. Okay. Just momentum conservation. Now, if you want to apply, what should I say, energy conservation law, then this you see these equations. Energy conservation law for this process, and in this frame, put PA is equal to minus PB and PC equal to minus PD in this equation. So PA, this remains this. PB square becomes PA square because of this. PC square, this is same as this. PD square becomes PC square because of this. So this is the, again, this equation involves only two momenta, PA and PC. You could have written in terms of PA or PD or PP, PC or PP, PD, any two momenta, any one momenta from initial particle, one momentum from final particle will be there, okay, in this frame. So the final appearance of the energy momentum conservation relation takes different forms, explicitly different forms in different frames of reference, but the total content of this, or total information content in these equations is independent of what frame you choose. The energy information content is the fact that energy is conserved or momentum is conserved. Thirdly, if you look at this scattering process, in the center of, sorry, it is not center of momentum frame, it is the left frame. Sorry, I missed the left frame. Left frame means where one particle PA is at rest and B particle is approaching towards it. This is the another setup of laboratory setup of scattering. A particle is at rest, B is approaching towards it. Okay, so this is the initial setup, target and incident particle setup. There, linear momentum gives conservation. Linear momentum conservation gives you this, which means this, because PA is 0. Okay, PA is 0, so you get this, which means PC and PD outgoing, final two outgoing particles momenta, their vector sum should be equal to incident particles vector sum. Okay, so it should be like this. These two vectors should add up to give you this initial vector, which is shown here. This PV is a sum of PC and PD. Sum is done by here, showed by rule of, what is called, trapezium or whatever, parallelogram rules. Sorry. Similarly, energy momentum conservation, general form this, for this frame, you put PA equal to 0, you put PA equal to 0, and in place of PB, you can replace PC plus PD. So this form takes PA MA plus term plus PB is equal to PC square plus PD square plus MB square and this. So finally, also the energy momentum, here also there is a mistake. This is PD. Sorry, I copied the same equation. So
there also there should be plus sign.
Huh?
Plus sign before the MB square in the last line.
Plus sign before
MB square.
Yeah, sorry. Okay, sorry. Plus MB square, sorry. Missed it. But correct it before sending it to you. Remember, so this is the energy momentum conservation sorry, energy conservation equation. But see that this energy conservation equation in this frame, only energy conservation is this frame, has the term PC.PD because of this square. PC.PD carries the information of angle between the two outgoing directions here. So this is PC and PD. So suppose this is angle is theta. So PC, sorry, this is theta. So PC.PD is magnitude of PC into magnitude of PD into cos of theta. So the angle between these two outgoing particles direction is somehow appearing in the energy conservation relation, but not in the momentum conservation anyway. Okay, so some constraint you can find out from on this angle just from energy conservation. Similarly, from if you see the previous expression, I have not told it here. I told you that time. Where here also this plus sign was missing. This is because of this dot product PC and PD. The angle between these two particles are there here. So at least from energy conservation, you can say something about the angle, not all, but some bound on this angle you may get to conserve this energy momentum conservation. Okay. If you change PC.PD value, meaning if you change the angle between them too much, this may not get conserved for a given values of magnitude of PC and PD. That means for only for certain angles, this energy momentum, these energy relations can be conserved. Okay. So all these are there in these small things are there inbuilt in this energy conservation equations. So we now can handle the application of energy momentum relation for all these particles in different frames. For decay channel and scattering channel, in different conveniently chosen frame, you can apply this. You can also convenient, depending on your specific customization, you can choose your frame of reference, which may be convenient for your problem. Okay. So for decay and scattering, like there can be a scattering where there are 2 particles and like 7 particles in the final state. 2 particles in the initial state, 7 particles in the final state. When there are so many particles, you may try to find a more suitable particle reference frame to describe your energy momentum dynamics or kinematics. Okay, so this is all about application of energy momentum conservation. Actually, this ends discussion on conservation of intrinsic quantum numbers and these extrinsic parameters like energy and momentum. I will not continue. Today I want to end this class here. I have some meeting now. I have to join. Next day we will start discussing about baryon numbers in more detail, or in particular where we have to discuss a huge spectrum of particles which are not fundamental but which are observed freely in nature. Okay, like proton, neutron, but they are only 2, they are not fundamentals. But from their description, from the list of, so far we have only seen fundamental particles. So we have seen means I just introduced them for this introduction to this course. Now we will gradually see how things develop. For that, I am giving you a set of problems which you can try to do. These are just copied from the 5th book. You do not need to submit it right now. I will tell you when to submit. Just take your time and look at the energy momentum conservation relations and see whether you can do the analytical part involved in these problems. So be a bit, so practice this so that you can handle this application of energy momentum conservation to different processes. Okay, so these problems I have given this one. Particularly these first two problems are very interesting problems because the results obtained from this problem are extensively used in many discussions which will follow, or I have already used it without telling you in the last class. You will see what that is. So there are three problems. You just try to answer, try to solve this. If you find any problem, because right now I am not finding any time to check all your problems, so I am telling you not to send it right now. You can send me at some point of time, I will tell you, but right now don't send me. You can solve it and keep it with you. If you find any problem, you can tell me where you got stuck or what to do. You can discuss among yourselves also. This is not an exam. Okay. So I'm sorry that today I have to finish early because so tomorrow, not tomorrow, when on Thursday, we will begin on, or what should we say, we will enter into the domain of particle physics fully. Now we have just knocked the door by and have had a plan how what the inside of the house is. Now we have to walk through the house. Okay, and the list which I have shown to you earlier, that this list, how this list came from observations and from logical arguments, particularly the second part, how these quarks, so I told you that quarks are not free, so how they are discovered or how their existence is predicted, all these things we will discuss in classes to come, and there are much interesting things involved in this part. Only leptons play only a very so far as volume is concerned, this leptonic part is a very small part. The most enriched part involving various physical quantities is, or dynamics, are this part of the other particles which are made up of quarks. And quarks are not fundamental, quarks are not composite particles, they're fundamental particles. But protons, neutrons, and so many particles are there. From there, we will see. Now we will see how we experimentally detect them a bit. That we will see, discuss a bit, and from how the experimental data, we analyze the experimental data to draw conclusions. Now we will not say how these baryon numbers are being assigned. Okay, one by one, that we will see. Here I just, for lepton numbers, I just, lepton sector, I just give a, I just told you yesterday how lepton numbers are assigned. Baryon numbers are also assigned in the same, following the same scheme, but those interactions from which baryon numbers are assigned to different particles, how quark gets 1/3 baryon number, 2/3 baryon number, those discussions need more involvement. Okay, so let me stop here. Or you can ask me if you have any question regarding today's class or previous classes, whatever. Hello?
Yes, sir.
Okay. So if you don't have any question, then I am finishing here, stopping here.
Sir?
Yes.
Hello. Sir, in processes involving fundamental particles, only we are saying that energy is conserved but not rest mass. So do you say energy or relativistic energy or mass energy? I mean, this is confusing me. The use of this term.
When I say, what confuses you?
I mean, what term should we use
Sir,
actually?
say
Energy or
when,
relativistic energy,
so
mass
in
energy.
whatever term you may use, but you should be completely aware of what you are using, what is the meaning of your usage. suppose in my course, whenever I say mass of a particle is m, that means rest mass. Okay. Whenever I say in particle physics, whenever you say in the physics of fundamental particles, whenever you say mass of an electron is 0.511 MeV, that always means rest mass. Only thing is that the mass we use this in the value of mass, rest mass, we put it in unit of energy units by just multiplying it into c square. Okay. So mc square is a measure of mass m. Yeah, so this can be called rest mass energy according to my or standard nomenclature. This can be called rest mass energy or simply rest mass, because if you assume that you are trying to express mass in terms of energy units, that you can do, because mc square mass is equivalent to amount of mass m. So if you express m in term, if you see how much energy, in energy units, how much energy is contained in this rest mass m, then this is mc square. So instead of using m or gram or kilogram as unit of mass, you can use it, the energy unit, as to represent the mass. Okay. So when I say, suppose mass of a particle is 1 gram or 1 kg. Okay. So I can say this mass, rest mass of the particle is 1 kg, or we can say that this rest mass is equivalent to m into c square, which is 3 into 10 to the power 20. Okay, c square is this 20 or 16 meter per second square. Okay, so this is c square. This is meter per second square. So we can say 1 kg of mass is equivalent to 9 into 10 to the power 6 joule of energy. Okay, now I adopt the joule of energy to use unit of mass to express mass. So when I say that the rest mass of the particle is 9 into 10 to the power 16 joule, okay, that means what I am referring to by rest mass is the basic energy content in the mass. Okay, see, this is the simple example. What is the distance between Belur Mott and Howrah station? You can say this is the distance is 4 kilometers, or you can say this is half an hour by taxi. Okay, so you are using time units to express distance. Just the time is how much the taxi takes to cover that distance. So the time equivalent of that distance can be used to express a distance. Like, so my home to my place to your place is 5 minutes walk, 5 minutes distance. We say 5 minute path. Like the distance is expressed in terms of time. Okay, in terms of in second or minute, because that 5 minute here refers to basically the distance covered by you in 5 minutes. So basically it is a distance. Here also the energy, what I am saying, when I am saying rest mass energy of electron is 0.5 MeV, I am quoting an energy value, but that energy value is equivalent to some mass relativistically, and that mass is electron mass if you express it in terms of kg. Is it clear?
Yes, sir.
Actually, I will next day I will discuss a system of unit which is called natural system of units. You know this natural units where c is equal to 1, h is, you know this, or have you heard natural units in any of the courses?
Yes, yes. Yes, sir.
So, okay, so what is natural unit? instead of choosing length, mass, and time as fundamental quantities and expressing all other quantities in terms of length, mass, and time, you choose velocity and angular momentum as fundamental quantities. And so not just choosing the fundamental quantities are enough. You have like length and mass, you have to set the unit, you have to fix a specific amount of that quantity as a unit. Okay, so when you say length, mass, and time are fundamental units, then you say that this amount of length I will decide to be 1 meter, this amount of mass I will call 1 kilogram, like this. Similarly, in a completely different way, since there are 3 fundamental quantities, you can choose velocity and angular momentum as fundamental units, with velocity of light taken as 1 and Planck's constant, which is the dimension of in angular momentum, taken as 1. Where this 1 means this is not 1 meter per second or so. This C is 1 means this is you choose velocity from the very beginning. You choose velocity to be dimensionless from the very beginning. Okay. You choose angular momentum to be dimensionless from the very beginning. With this choice, you start developing your investigating what the form of other quantities. Why this is allowed? Because C and H are observationally or observer independent quantities. See, what is C? C is equal to some time delta t divided and over, so distance traveled by light in time delta t divided by delta t. That is C, velocity of light, distance traveled by light in a time delta t divided by that time. That is C. Okay. So it is distance by time. Now, C is something, you see that is the independent of observers. So any observer, C is light to move with the velocity C, whatever be their velocity. Whatever be the observer's velocity, or to all observers, light appear to move with the velocity C. That means velocity of light is observer independent. Therefore, look at this relation now. Therefore, this is delta x by delta t. Okay. Suppose there is some distance delta x. You are measuring a distance delta x. Okay. You are calling that distance as some distance. You are calling this as delta x. Now, suppose you can call this is something, this distance amounts to delta x units. Okay. Now, instead of expressing this distance by a number and a unit, which is a chosen section of this length, instead of doing so, you can think of how much time light takes, because light is a universal object, universal velocity light does have. So how much time light takes to move this distance? Okay. So how much time it takes? Suppose it takes a time delta t. Okay. Now suppose you call the distance between these 2 points is, or the time taken by light to move from A to B is a measure of the distance AB. Is it clear? The time light takes to move from A to B, that amount of time is a measure of the distance between A to B, because if A to B is greater, delta t will be proportionally greater. So in that sense, delta t itself can measure the distance, because velocity of light is uniform and it's same to all observers. Whoever sees it, any observer, whatever be their velocity, they can say that the time light takes to move from A to B is, I can take that as a measure of distance between A to B. Therefore, what is the velocity of light in this measure? Distance between A to B is the time, by our choice, the time light takes to move from A to B. So by our choice, velocity of light, which is the distance between A to B, which is same as the time taken by light to move from A to B. So this is one ratio of two same numbers in that way. So by defining length, by measuring length in units of time, because by virtue of using the fact that a fundamental velocity like velocity of light exists, which is observer independent, using that I can use length, or I can use time to measure length, or vice versa. Then velocity of light, which I use to define this kind of length and time equivalence, that velocity of light itself in this system becomes one, and this one is dimensionless. So velocity, you can think of velocity to be dimensionless. So when c is 1 means dimensionless, and in this unit system, length and time doesn't have any independent existence. They are one. They are one in the sense that length and time has same units. Now you can choose, if you choose centimeter for length, you can choose centimeter for time also. Or if you choose second for length, you can choose second for time also. Okay, this is natural system of units. I am using this natural system of units here. Actually, I will discuss this with more clarity in next class. Then your things will be clear. But to answer your query, the fact is that just a minute, a particle which has mass m and this quantity p square momentum p, if it p square plus c to the power 4, this is equal to E. Okay, so this is the relativistic energy momentum relation. Now you can, what I have done so far, I have this PC, okay, I am working in a unit where I am choosing C to be 1. What does it, why I can choose it, I will describe, but if you just put C equal to 1, this is P square plus M square. Okay. Now this is E. So this whole PC I am calling momentum square of the particle. The whole mc square I am calling mass square of the particle. Mass of the particle. Okay. So in that, so if we, because C is just a constant. So if we just multiply m by c square, and that becomes energy, but that energy I can take to represent some mass m. Okay. Similarly, if I multiply momentum by c, I get some energy dimension, but that quantity with dimensions of energy is a representative of amount of momentum of the particle. Clear? And E is the total energy of the particle, which is square root of this. So if you, which is in other words, this means I am choosing C equal to 1 for this case. Okay. Is it clear? At least. This is the same way as we say when we say that what example should I give? Like that distance you express in terms of time. you say 5 minutes walk. So you are covering a distance in terms of time. Okay. But that 5 minutes walk means your velocity of your u is involved in that. You have divided by that distance by your velocity and say that this is 5 minutes of walk. But your velocity can change with different observers. Different observer can see your velocities differently, so that distance description can change. But velocity, light is one thing whose velocity is same for all inertial observers. So at least all inertial observers will see light to move with same velocity. So if they divide the distance between 2 points by the velocity of light, they will get some amount of time. And that is the time light takes to move from one place to other. And that time itself can be taken to represent that distance. Okay. So in this system of unit, length and time has same distance, same dimension. Therefore, energy and mass have same dimension. Momentum and energy and mass, all of them have same dimension. Okay. I will discuss this in more detail in next class. Okay, so let me stop here. Or if any other questions, you can ask also.
Sir, I got this, but when we say that rest mass is not conserved in a process involving fundamental particles, so does it mean that rest mass, its equivalent energy? Um,
just a minute. So look at a process. For example, this is the process. So look at this process and this process. So this tau particle, this is, look at any suppose this decay channel. Okay, tau goes to this particles. Now tau has a rest mass, this, and all these particles, these are almost zero, and this has a rest mass. So first thing is that you observe this decay, and you see that rest mass of initial state is not equal to rest mass of final states. What is only conserved? The conserved quantities observationally are momentum and energy. Okay, but relativistically, if momentum is conserved, if energy is also conserved, then rest mass cannot be conserved. That you can also show from what I've seen here. Because if you look at this equation, if this equation has to be true and this equation has to be simultaneously true, then you cannot have MA equal to MB plus MC plus MD. You can check this. This equation 1, 2 and MA mathematically, even mathematically, MB plus MC plus MD. First note that this three equation, conservation of momentum, conservation of energy and conservation of rest mass, these three equations can never be satisfied simultaneously under any condition, because the form of mathematical expressions are like that. Okay, this is one thing. Second thing is that experimentally you observe for all interactions in nature, linear momentum is conserved, and for all interactions in nature, angular momentum is conserved, and you observe that for all interactions, rest masses, sum of rest masses and is not conserved. That is also an observation. Now you try to realize that if energy is conserved, that means this particle A has two parts. One is this part, M. This is the rest mass energy part, and this part of energy comes due to momentum. Okay, square root of this. So E square, better to see this. E square is P square plus M square. MS square is square of the rest mass. P square comes from the momentum, kinetic part of this. So total relativistic energy of a single particle A has two parts, rest mass and its energy due to motion. Now when A decays, all the total energy of the particle, including the rest mass, the total energy contained as rest mass, and the total energy giving momentum to it due to its motion, the entire energy gets deposited to the universe, and the particle A uh, is dead or loses its individuality. Okay. Now, when this total energy, particle A is losses, total energy content of a part of it is rest mass, another part is energy due to motion, that energy becomes free. Okay, and now once becomes free, now there is no distinction between rest mass part and momentum, because a particle is not there. Existence of a particle was only separating the rest mass and momentum kinetic energy part. Once a particle is annihilated, the full energy is free. Now new particles are producing from it, from this full energy, keeping energy and momentum conservation. Means B, C, D comes out with their own momentum and with their respective rest masses, so that total rest mass and total energy of each B, C, and D, where total energy of every particle contains in it its rest mass and its momentum. Its rest mass and its momentum. Its rest mass and its momentum. Their sum should be equal to this total energy. That is the condition, conservation condition. And also, total momentum, so far as direction is concerned, has to be satisfied. That is observationally seen. If these two are satisfied, there is this MA need not be equal to MB plus MC plus MD. Okay. Because what is conserved is energy, total energy and total momentum. Rest mass energy are only a part of it. When the A particle decays, its rest mass energy and energy carried by A due to its momentum got mixed up. Now there is no distinction. From this, B particle, C particle, D particle are born with their respective bond. When each particle is born, within them, they take some energy as its rest mass to have their existence, and some energy as their momentum to fly off. Okay. So this total energy of B, including rest mass and momentum energy of kinetic energy, plus total energy of C plus total energy of D should be equal to the total dissolved energy of A. That is the condition. So 1 and 2 are the conditions which does not require, or if these two are satisfied, you cannot satisfy this in general. Is it clear? There is only one situation, one hypothetical ideal case where you can think of validity of this equation, where all the P's are 0. Then PA, PB, PC, all the momentum particle are 0. Then you see, then this conservation holds 0 plus 0. And then also PA, PB, PC, PC 0. Then MA equal to MB plus MC plus MD. That means if particle of mass MA was sitting at rest, then it disintegrates to produce two particles with masses, 3 particles, MB, MC, MD. All of 3 are also at rest. Okay. Only in that hypothetical condition, this rest mass energy conservation will be satisfied, because rest mass energy conservation at that time is just the energy momentum conservation, total energy conservation, because momentas are 0. But in general, when all these particles, in nature, particles masses are such that they are too small, and initially when a particle decays, these particles B, C, D have their momentum. Because of that, their mass could not be made sum to just rest mass sum could not be equal to this, because they have other masses. Okay. Am I clear? Is it clear to you now?
Yes, sir, I get it.
Okay. Anyone? Okay, thank you then. I will send this file. And with this, yeah.
Sir, the reaction, the E plus positron, electron neutrino and muon neutrino coming together is less probable. Why is it so?
Just Where is it? Here.
Processing.
The last equation.
Yes, yes, sir. Yes.
Because in nature, there are these three microscopic particles, free particles, E plus mu is the probability of that these three particles are at same place are much less compared to probability of two particles come together. What I am saying is that probability of occurrence of this last reaction is much less than the other four. Because for this reaction to happen, this E plus and these two news has to mingle together. I mean, come to be very close proximity. Otherwise, this reaction can't. This cannot happen when this E plus is in sun, this neutrino is in earth, and this antineutrino is in moon. This reaction cannot happen. They will dissolve to disappear from nature. They have to interact together. Interacting means for fundamental particles, they have to come within this closed zone. Say within this closed zone, this A, B, and the other particle C has to come. Now, in nature, this is obvious that three particles coming together is much less probable than two particles coming together. Okay, at same time. Suppose
Is it true for all? Is it true for all particles or just for these?
No, all particles. All particles. This is a generic statement of, what should we say? That second law of thermodynamics. That this is a more, disordered state, initial state. You have to do much more energy. You have to do, or what do we say? You have to do much work to put three particles together at same time. It's true for all particles. Even in the laboratory, if you want to no, what I am saying is that, just a minute. What I am saying is that, where does that go? This equation, where does it go? Oops. Here. Okay. So somehow say if you are God and if you can bring all these particles together, then it is okay. This reaction will happen. If there is a constant supply of E plus, mu and mu bar at one point, then this reaction will happen. The rate of this reaction will be as good as this rate of this reaction. But that supply, to get this supply is less probabilistic. So this reaction rate is faster, but what I have said that there is a less probability that three particles are coming together. That probability is always less. If there are four particles, there is much lesser probability. Because all particles are moving randomly. Even if you try hard, if you try in the laboratory to collimate these three particles to put together, you have to do a lot of work. To overcome these less probable natural things. Okay, to bring two particles together, you have to do work, but you have to work with two particles. Okay, suppose you can say in geometry you can draw any two straight lines. If they are not parallel, they will intersect. Any two arbitrary straight lines you draw, if they are not parallel, they will intersect. Means they will interact at any point. But that means any two particles coming from any directions, if they are not parallel, their path length, at least path length should interact. Okay, their trajectory should interact at least. Now if you draw a third straight line, what is the probability that third straight line will pass through that intersection point of two straight lines? That probability is very less. if you try to draw random straight lines, the probability that two random straight lines will intersect is very good probability. They're very, because they just have to be unparalleled. But for a third line to draw, which will pass through that intersection point of two straight lines, that probability is very less. That is the same argument. Because of that, in nature, all particles are moving. There are few probabilities that two particles interact, and suppose there is some probability that two particles come to say very close to each other at some point of time. With respect to this probability, in the same ambience, probability that three particles will come to that point at same point of time, that is very less in general. Okay.
Okay, sir. Okay.
That is nothing to, but there is another thing called strength of this reaction. That strength of this reaction is very good. If you have supply of this constant supply, this reaction will continue to happen. Suppose you don't have supply of mu minus and E plus anywhere in nature, this will not happen. But if you have supply of these three at same point, this reaction will keep on happening. This will not happen because of you block the supply. Okay, but in normal conditions, when there is no lockdown, in normal conditions where people are moving randomly, then this is much less probable than this because of this two particle state and three particle initial state. Actually, this is called a phase space suppression. These two particles, actually you will see these in detail in particle physics course, in quantum field theory course. This is how this aspect comes. There are more particles. It is like you are you have a shelf and you are packed up books, and you are moving out one books from the shelf of the library. Okay, so it is always easier to bring that book out of the shelf. Once you move that book out of the shelf, now if you want to put the book back on the shelf, now you have to do some extra work, because then you have to put exactly the book on the exact location. So in the first process where you are we are taking that book out, then the book is coming from a smaller space it was occupying to a larger space. Larger space is the whole space where the book is coming out. So that makes that transition is easier than the reverse transition where you are putting the book from a high volume, from more space to a compact space, in the space of the book where the book was initially there. You are putting back the book there. Then you have to work very hard. Clear? Because anyone can take out a book to put that book there. You have to do take more care. So it is so when particles are is this analogy suitable here? No, that is for a different analogy. That is not suitable here. Anyway, sorry. That will not be suitable here. That will be suitable for a different analogy. I'm sorry. Sorry. Okay. But you understand this point, right? This is just bringing three particles together is a tough job.
Yes, sir. Yes, sir, I understood.
But these are important points, actually, important points in the sense that when you calculate the total cross-section of the process or lifetime of the process using field theoretic calculations, these aspects you have to consider, that how many particles are there at the initial state, what is the effect by reducing the particle number from here to here. Those two are fundamentally same processes because all are related to this same set of lepton numbers are conserved. But just because of number of initial particle, number difference of the particles in the initial and final states, there will be difference in their probabilities. Okay, let me stop here.